Hello, 1, 2, 3, good. Okay, hello, it's good to be back. We're talking about the second section of the first chapter, Functions, Graphs, and Limits. This time, we're going to talk about graphs of equations. Here are some of the things we're going to talk about. Nothing real complicated. One of the most important parts is to use mathematical models at the end. And we'll work up to that. So the graph of an equation, let's see what we've got. Okay, first of all, sometimes we have two different quantities and we've got a relationship between them. For example, temperatures on the Fahrenheit scale are related to temperatures on the Celsius scale. We're going to see some procedures for graphing those relationships, and here we go. So here's an example we can start with, and I'm going to set up my pen here. I'm going to stick with the red. Seems to stand out pretty well. The idea is to sketch the graph of y equals 7 minus 3x. And my first note that I actually put in the slide here is that if I were doing this, I would probably write it this way instead. I would take the 7 minus 3x, write it this way instead. Why would I do that? Because in function notation, it would actually look like this, and I would prefer it to look like this, because here's the constant part and there's the variable part. When x changes, it gets multiplied by minus 3x. 7 is always added at the end. That's constant. The way to sketch the graph is to make a bunch of points. So you pick some x's that seem to make sense for this particular function. Just put them into the calculator and you can find out what each individual y value is. Now, I'm going to use the TI-84 as an example. Now, if I'm using the TI-84, please ignore those extraneous lines. Sometimes they do show up like that. The way you can do that, or one way you can do it anyway, it's not the only way, is that, for example, if you want to use 0 for your x, you can type in 0 on your calculator and then hit the store button, which looks like this on the screen. Then type your x button, and what you'll get is a verification that you put a 0 in. Now that doesn't seem to be that great, but then what you can do is you can type in the actual function, and it's going to use the 0 that you just put in for x. So that's going to give you the value of 7. You want to get the next one? Take 1, store that in x. You don't have to retype the minus 3x plus 7. You can just cursor back up, bring this back up on the screen, hit enter, and the next thing you know, you've got the value 4, and that goes with an x value of 1. A little bit sloppy, but I'm still working on my skills using the graphing tablet. You can do that just by changing the x value and typing your function in again, seeing what the function value is. There are a couple of other ways of doing it. If you're interested in what I might consider a little bit faster, here's a tip. come to my office and I'll show you another way of doing that. And this is by using the y equals button on your calculator, and I'll leave it at that. There's another way. You can also use the table function inside your calculator. Anyway, let's move along. So you get a number of ordered pairs. Here's an ordered pair, there's an ordered pair, there's an ordered pair, and there, and there. So here's a little bit of a summary of what I just said. 2, store in an x, then type the 7 minus 3x, the function, and you get the y value. Another way is by using the y equals key. You can put the function in there, and then you can type in y, whatever it is, parentheses, put the x value you want, second parentheses, and you can get it. Stop by my office if you're interested. It can be even faster. So that first order pair says that's the solution point of the equation. And when you put the other ones in, you get 3 more points. Graph those points. And this is what it would look like. There are your points with big dots. Sketch the graph of x squared minus 2. Not so difficult. Create a table of values. Now, to be honest, I do it a little bit differently. Maybe it's just, oops, oh, crazy there. Maybe it's just because of whoever taught me the first time showed me this way, but I tend to put the x's in vertically and the y's in vertically, and of course line them up properly. And then take those ordered pairs and put them on my Cartesian coordinate system. There are your points. Your job then is to connect them. Now if we sneak back here for a second, notice our function was y equals x squared minus 2. The x squared should give you a hint that this is not a line. Lines have first degree x and y coordinates. This has a second degree x coordinate. So actually this is going to end up being a curve. In particular, it's going to be a parabola. If you haven't done much of this before, with a little bit of practice, you can get a nice smooth curve, or pretty reasonable anyway. Not perfect, that's not what's important. What's important is getting a feel for how the x and y's are related to each other. All of the parabolas have this basic look to them in one form or another. Y equals ax squared plus bx plus c. The only reason it says a is not equal to 0 is because if a is 0, then you don't have a parabola, period. You just have a straight line. So that's not a big deal. A, B, and C just represent real numbers. One big thing to remember is that, where's my cursor? There we go. If that first coefficient, the A, if that A is positive, your parabola is going to open upward. If that first coefficient is negative, then it's going to open downward, sort of like that. Well, that's not too good, but you get the idea. Next, intercepts of a graph. Well, there are 2 intercepts we're interested in because we've got a Cartesian coordinate system, and that Cartesian coordinate system has x values and y values. As well as being called the Cartesian coordinate system, you might refer to it occasionally as the xy plane, in case you're working with just x's and y's. So if you do have two coordinates like that, you're going to have two axes, the x-axis and the y-axis, and the intercepts represent where does the actual curve or line cross the x-axis or the y-axis. The x-intercept means where does your curve, where does your function cross the x-axis. The y-intercept represents where does it cross the y-axis. Sometimes we'll represent the intercepts by an ordered pair, sometimes just by the number itself. It should be self-explanatory when you're talking about them. So here are a few examples. On the first one, take a look at that. It does not cross the x-axis, so it has no x-intercept. It does cross the y-axis right here, so it does have one y-intercept in this case. In the second graph, how about the x-intercepts? Well, it crosses the x-axis here, and here, and here. It's got three x-intercepts. Y-intercepts, it crosses the y-axis at that point right there, one y-intercept. You'll notice that one of those intercepts is both an x-intercept and a y-intercept. That can happen. But it's easy to tell what your x-intercepts and what your y-intercepts just by eyeballing it once you've got the graph. Next one, if you take a look over here, it has one x-intercept. That's the only place it crosses the x-axis. It has two y-intercepts where it crosses the y-axis, and this next graph doesn't cross either the x or the y-axis. That can happen too. In fact, you might take note of the fact that this particular graph is not even a function. Remember functions? Well, functions have to follow the let's just move on to the next one. Okay. So, sort of your cliff notes, if you want x-intercepts, there we go. If you want the x-intercepts, let the y be 0, and then solve for x. If you want the y-intercepts, let x be 0, and solve for y. Those are two good tips to keep in mind. Put those on a 3x5 card or something, carry them around, take a look at them occasionally until they become second nature. So, what about the x-intercepts and y-intercepts of y equals x cubed minus 4x? Well, go back to your notes. If you want the x-intercepts, set the y equals 0. If you want the y-intercepts, let the x be 0. So, here we go. X-intercepts, let the y be 0. So, your graph of This becomes that because the y is 0 for x-intercepts. Take this equation, solve for x. You can solve it by factoring. There's a complete factorization. Set each one of the factors equal to 0, and you've got 3 x's. And remember, y equals 0, so this gives you 3 points. 0, 0, negative 2, 0, and 2, 0. 3 points, 3 x-intercepts. If you want the y-intercepts, let the x be 0. So in this case, we take the original equation and put the zeros in where the x was. And very simply, this gives you 0, and this gives you 0, subtract, you still get 0. So you've only got one solution for that equation, so you've got one y-intercept at the origin in particular. There's a picture. Notice the 3 x-intercepts, x-intercept, x-intercept, x-intercept. The y-intercept, only one of those. Circles. So we'll do something a little bit different. We're talking, remember, about the way the x's and y's are related to each other. Well, for circles, we're talking about a point as a beginner. To have a circle, you start at the center. That isn't part of the actual circle. The circle is all the points that are given distance away from that center of the circle. Now we talked about the distance formula last time, and the distance formula, remember we have the subtraction here, and we also have the square here. Using the distance formula, you get the distance from the center to any point out here, h, k. If you square both sides, this is what you got for any circle at all. Here is the standard form of the equation. The beautiful thing about this is, if you write it this way, just by looking at it, you can tell where the center is. The center is at HK. Center at HK. No secrets there, and you can tell what the radius is. If it's in the form r squared, r is the radius. If it's not already obvious, then if this is a 25, for example, you'd have to take the square root, and 5 would be your radius. Now the second part of this special rectangle of information says if the point for the center is actually at the origin, then the equation of this circle becomes x squared plus y squared equals r squared. Well, this might be handy to remember, because that is a special one. You don't have to put the 0 in there and clean it up. This one only is the one where the center is at the origin now. So it's a unitasker, as they say. The one up here is for all circles, not just one with the center at 0, 0. It's up to you whether you want to remember the second one by memorizing it or not. But you do need to know the first one. Now, we've got a small problem here to work with, and we've got a point 3, 4, it's on the circle, and -1, 2 is the center of the circle. The question now is, find the standard form of the equation of this circle and sketch the graph. Okay, we could probably sketch the graph almost already if we just knew what the radius was. Well, first of all, here's the general form, because notice it doesn't have its center at the origin, so it'll look like that. We know what h and k are because, we know what h and k are because there's the center. So x minus a -1 will be x plus 1 squared plus y minus 2 squared equals, someone forgot to tell us what the radius was. Oops. Well, all is not lost. All we need to do is find out what the radius is. Use the distance formula. The distance, in this case the radius, is the square root of, remember the general form is x minus x1 for the center squared plus y minus y1 squared will give us the r, and we have 2 there. We've got x coordinates, y coordinates. So let's see what we've got. R equals square root of, make that big enough so we have the room. We need to subtract the 2 coordinates. Now we're talking about 3, 4, and -1, 2. So if I subtract the 3 minus the -1, that gives me 4 when I subtract the x coordinates. When I subtract the y coordinates, 4 minus 2 is 2 squared. R equals 16 plus 4. R equals the square root of 20. And if you were a real purist, you could simplify this a slight bit. This might be going a little bit far in this case. Square root of 20 is what we need. So if I bring this back here, what I've got is x plus 1 squared plus y minus 2 squared equals, and the r squared is 20. And there's my equation. That's in standard form. And now we can sketch the graph. If we want to sketch the graph, we know that the center is at -1, 2. So -1, 2 would be something like this. I'm not going to put the hash marks in. And we know that the radius is the square root of 20. And the square root of 20, roughly speaking, where's my cursor? square root of 20 would be 4 point something. You can check that out on your calculator. So somewhere out here, there's our center. 3, 4 would be about there, and circle would look roughly, very roughly, something like that. So I got the radius first, square root of 20, put the coordinates of the center in, and the radius, and there's your equation. Oops, there's your equation in standard form. There is your answer. And there's the picture, a little bit better than what I did. But remember, I didn't have a nice set of axes and everything to go with. Points of intersection. So now we're talking about having two different equations. Two equations. Of course, if they're the same equation, that's sort of silly. They have all their points the same. For two different equations, the point of intersection is where the two equations have the same x and the same y, satisfying both equations. So, why do we care? We care because it's a good business application. This involves the break-even analysis. Break-even, you can think of it a couple of different ways. First of all, when you're thinking about a business, revenue is the money coming in. Let's write that down. Oops. That's the money coming in. Cost. Money out. Now the break even, a couple of ways of looking at this. One is that the money coming in and the money going out are the same. Revenue equals cost. In other words, if you think of it in terms of a cash register, the money coming into the cash register equals the money you're going to have to pay at the end of the day to pay your employees, to pay for the heating, light, and all that kind of stuff. Another way of looking at it is this, and this will prove handy this semester. If you're thinking of the profit, perhaps you're thinking, gee, at the end of the year, I wonder if I'm going to have enough left over so that maybe I can make that vacation that I wanted. Well, the profit is the money that comes in minus all those checks you have to write. What's left over? Well, to break even, that means the profit is zero. You don't make money, you don't lose money. Or R minus C equals 0. Two ways of looking at the same thing. You can tell that this equation and that equation are the same. Revenue equals cost, or revenue minus cost equals 0. Either way, you're breaking even. The bad news is you're not going on that vacation. The good news is that you're not losing money either. Money isn't coming out of your wallet. That's the break-even point. If you sell enough so that the revenue offsets the total cost, then you're breaking even. Just showed you that one, cost equals revenue. Frankly, well, you can write it whichever way you want to. I tend to write it the opposite way. I guess accentuating the positive instead of the negative, whatever. Okay, we've got an example here. The company manufactures a product, and that product costs 65 cents to make each one of those items. They sell each one of those items for $1.20. And the company's initial investment, maybe research and development, was $10,000. How will the company break even when it's, or will the company break even when it sells 18,000 units? How many units does it have to sell to break even? Okay, first of all, I'm going to start with the cost. Because before you can actually sell anything, you have to have the item in your store to be able to sell it. You have to pay the rent for the store. You have to pay a lot of things for the store. You have to make sure it's heated, especially this time of year. So what's it going to cost for your first month, for example? Well, first of all, to get your product to the store at all, you have to spend that $10,000. That was your initial investment. What else? Before you can sell anything, you've got to bring those items into your store. Each one of those items is going to cost you 65 cents. So just think for a second, if each one of those items costs 65 cents and you decide I need 100 of them in my store, then what's it going to cost you? 65 cents times 100, $65. If you have 200, it'd be 65 cents times 200 and so on. If you've got X items, at 65 cents a piece, it's going to cost you 65 cents times whatever number of those items you need to sell today or this month or this year. That's going to be your cost. This is called fixed cost because it doesn't change. This is called the variable cost because it depends on how many items you want in your store. Next, that's how much the cost is, the total cost. Put that out here. Total costs. How about the revenue? What's the money coming in? Well, each of those items you're going to sell for $1.20. And you're going to sell X of those items, $1.20 each. So how much money is going to be coming into your cash register? $1.20 times however many of those you're selling. And this would be total revenue. Now, we're talking about breaking even. Breaking even means revenue and costs are exactly the same. So that means in terms of this, here's the money coming in, and here is the money going out. In, out. Well, we've got an equation here. We can solve that. $1.20, make sure the decimal point's there. I'm going to subtract 0.65x from both sides. Okay, so what's that going to give me? 5.55x equals 10,000. Put a 0 out here so we recognize that the decimal point is there. So x and we can find out how many we'd have to do to break even. Now we can actually figure out the first part of the question before that. It says, will the company break even when it sells 10,000 units? So let's sneak back here. I guess it's not going to let me. Okay, so here's my equation. We're going to see what happens when I've got 18,000 units. So I'm going to take that equation and I'm going to put 18,000 in where the x is. So $1.20 for each item I sell. And we're assuming we sell 18,000 units. And question mark here. Remember, this is the revenue. It's going to be the cost over here. And the cost is 10,000 plus 0.65 times that 18,000 items that we had to buy to bring into our store. Now you can't see what I'm doing, but I'm actually grabbing my calculator and I'm going to find out what that is. So if I take that $1.20 times 18,000, that means that if I sell 18,000, I'm going to have $21,600 in the cash register. That's the money coming in. Now how about this? 10,000 plus 0.65 times the 18,000 items we had to bring in, and so our costs would be $21,700. So what's the deal here? It looks like the money coming in is $21,600. The money coming out is $21,700. Oh, looks like we haven't gotten there yet. That means $100 is coming out of our pocket. We haven't broken even yet. We are not breaking even. Not good. What's it going to take to break even? We've already done most of the hard work. We'll take that 10,000 and we'll divide it by 0.55, and I'm going to need to sell 18,182 items to break even. And if I break even, I'm not going to be smiling, but I'm not going to be frowning either. Sorry, you can't see that too well, but hopefully you could see it before that. So there's the break-even point. There's the equation we had, the revenue on the left, the cost, the total cost on the right. There's the equation we got when we simplified by subtracting 0.65x from both sides. There's what I just did to find out how many I needed. And that's what I had. By the way, before I leave that, what I actually got for the break-even point was 18,181.81818 repeated. However, if I only sell 18,181 items, I don't quite break even. Close, but I don't break even. I need that one extra item, and then I'm past the break-even point. And there's a picture of the break-even, the cost, and the revenue functions. And that's where they cross. That's our break-even point. So two equations that you're going to see quite often are the supply and demand equations. The supply equation is the relationship between the price of a product and how many are supplied. P for the price, the unit price, and how many items there actually are. The graph is called a supply curve. It involves price though. Sometimes that's called the price curve. The demand equation shows the relationship between the price and demand. And the point where they cross is called the equilibrium point. Visually it looks like that. You can take those two equations, set them equal, solve for x. Model. And this table shows years and crude oil production from 2009 to 2013. What you see about 2/3 of the way down here is the mathematical model for these data. Y represents the production in millions of barrels. And T represents years after 2000. So 2009 up here be a T of 9, T of 10, T of 13. All that does really is just make it easier to work with the numbers. You could just as easily use 2009, 2010, and so on. Just as you could use 5,350,000 the crude oil production for the first one, and so on. But narrowing it down to smaller numbers makes it much easier to work with. So here's a graph that gives you an idea of what's going on. You can also tell by the model that it's a quadratic model because notice that it's a t squared. It's not a linear model. If it didn't have that square, then it would be a straight line. And that would be the simplest model and the easiest one to work with. It's not. This is more like a quadratic model. You can actually use numbers like this. These are the numbers we got. If you're interested, you could stop in the office. I could show you how to actually create that model. Now, the model looked like this. If you want to see whether it fits the data well, what you can do is, here for 2009, remember this is years after 2000, this would be a T of 9. If you take that T of 9 and put it into this model, the 9 in for the T's, just use your calculator, find out what Y you expect to get. The point is, does the model fit the data? How good a fit is that model? Well, if you put 9 in and you get something close to 5.35, you've got a pretty decent model. If you put a 10 in and you get close to 5.48, your model's still pretty good. Put 11 in, see if you get close to 5.64, and so on. How close does a model come to your real data? That's what it's talking about. So if you want to know what 2014 might give you, just put the 14 in for those T's, and there's your estimate of what 2014 might give you in terms of barrels of oil per day. Last of all, we've got mathematical models of various sorts. A linear model, like this first one out here, would be a fantastic one. Now, if it goes through the origin, you've got a really unusually convenient model. If instead it does something like this, still not too bad, linear model, it's easier to work with. The quadratic model, well, at least you've got a model. It's not quite as nice as the linear model. You have to go through some hoops, so to speak, to actually work with the data, but it's not too bad. And the graph would look something like that with a parabola. On the third one, maybe instead of being a quadratic model, it's a cubic one. It might look something like that. It might be translated. Remember we talked about translation the last time? It might be translated. You might have a curve that looked like this, for example. Still a cubic, just translated from the original model. A third possibility is a square root model. Well, a couple of things you might notice about this. This square root model looks a little bit like a parabola. It looks like a parabola that you put on its side and erased half of it. That's what the square root model looks like. The fifth one, the absolute value model, looks like a V. It doesn't necessarily have to be at the origin, just like this one doesn't have to be at the origin. These are general looks. It does have a V pattern. It has a sharp point here, and this would be a good model for some kinds of data. Last of all, another one, a rational model, is based on something that looks like y equals 1 over x. In other words, something where you have a model where x is in the denominator. Knowing what these graphs look like might help you in the creation and use of some of your mathematical models. And I hope you've gotten an idea of what this represents with the models and some of the graphs. If you have any questions, remember you can always stop by my office when I get a key and chat about these or ask questions or send an email. Remember, if you have an email and you don't want to wait, you have two very quick choices. I really prefer email because that gives me a chance to think about the best answer for you and also to get back to you as soon as possible. The biggest reason for using that one is because as I'm concocting or creating some kind of response to your question, I can do a lot more things with using my Outlook than I can using a text or something like that. Please don't text. It has to be a real emergency, and really, in most cases, it would be hard to give you an answer. So there's an easy one, and of course, if it's a time critical one, if tomorrow's a test and you just need one question answered, give me a call, no trouble. Don't call me at 2 in the morning. All right, that's about all I can tell you right now. I hope you are doing well in the semester, and I'm looking forward to seeing you on our first Monday in class on the 11th. Take care and keep smiling. Bye-bye.